Thanks a lot for the introduction. Hope you can see my screen. Okay, perfect. Yeah, it's my pleasure to give a presentation here at the Machine Learning and Science Conference. Yeah, as already told in the introduction, I'm in the mathematics department in the mathematical optimization group. In general, we are working on optimization problems that are in one or the other way motivated from problems in machine learning, computer vision, or image processing. We have a particular focus on non-smooth optimization problems, so situations where you have certain problems with differentiability. And in the presentation today, I would like to formulate parameter learning problems, as you face it kind of always in machine learning, as a bilevel optimization problem. It's first of all just interpretation, it's a formalization of the problem, but which eventually gives us also some idea on how to solve these kind of problems. And in fact, this additionally takes a connection from classical variational models of classical inverse problems to the new era of parameter-based optimization and to data-driven models. So I'd like to start with inverse problems in general. So what is the inverse problem? The idea is we make some measurements, which is usually corrupted or noisy data. For example, in context of image processing, it could be a noisy and blurry image, as you see it on the right. And the goal is to infer the input. So what is the clean image, the clean information that we started from? And by knowing that there is some process which takes us from the clean image to basically the noisy or corrupted image. And the goal to reconstruct the clean image from the noisy measurements, that is what we call an inverse problem. In principle, the only idea is to invert the operator A, but in general, that's very difficult. Also, it's not a well-posed problem because you have the additional noise, and inverting is usually problematic. So we have to think about alternatives, and one idea that is usually pursued in this context is to try to invert the operator A as good as possible, but at the same time preserve or try to get some alignment with prior information. That can be done by solving optimization problem. To make the problem a bit more concrete, we could try to solve an optimization problem, as you see it here. We are looking for an image U that, after applying this process from the inverse problem, this forward operator A, is as close as possible to the noisy and blurry image F. So for example, to the image that you see in the middle. So that is the first term, often referred as a data term. And we have a so-called regularization term, which tries to restrict to solutions U that satisfy some prior assumption here, for example, smoothness. So the goal is to reconstruct the image F as good as possible, it's the first term, and at the same time make the best compromise between reconstructing a natural image, which is here measured by just the smoothness term that penalizes differences of the color values. So the reconstruction that we could achieve from the blurry image in the middle would be reconstruction that you see on the right, and that is supposed to be close to the clean image. Of course, meanwhile, there's also better approaches, but Okay, there's many other problems. I would like to mention a few more. For example, depth map fusion. Here, the setup is the following. You have measurements Fi, which correspond to depth maps from a certain viewpoint of a 3D object. These depth maps are not complete because they are mapped. They have some occlusion that is that we have to deal with, and we have to infer a full depth map, and so also a 3D reconstruction of the surface that you see in all of the images. And again, we have this data term. Here is the first term, and we have some regularization terms. And I would like to start putting emphasis on the parameters. So there's also parameters lambda1 and lambda2. But before I come to the parameters, let's look at another problem, machine learning problem, matrix completion problem that you see in collaborative filtering applications. So one application could be to infer ratings for movies. So let's say A is a matrix where the ijth entry of A is the rating of user I for movie J. And you have this information, so not all the users have a rating given for all the movies, but just for a few of them. And therefore, we have this additional projection operator, which restricts to the information that is given to us. And we would like to reconstruct the ratings as good as possible, but we want to get a full matrix, the full matrix X, which from the few ratings that we have infers a full matrix. So which can give to any user a rating, and in this way also make suggestions. That can be achieved by, first of all, minimizing this data term and additionally minimizing the rank of the matrix X. And minimizing the rank of the matrix X can be done by a nuclear norm and other things. These are technical details that are not so important for the presentation here. We have in general a structure of the form. We want to minimize some objective function E, which depends on a parameter lambda. It consists of a data term and a regularization term. And we have this regularization parameter lambda. And now the parameter learning that I'm talking about is how to find a good lambda. Of course, what is directly connected to the question, how do I judge what is a good lambda? Of course, here the idea is for a certain lambda, I can make the reconstruction. From the blurry image, I can do a reconstruction, which is a kind of a clean image, and I can compare it with ground truth theta and therefore try to get a good lambda. Or I just look at the image and I try to adapt the weight lambda. If we have just one parameter, it's no problem. We can do it by hand tuning. We can also make an automatic process out of it by some grid search, some other search strategies. Regularization rate is really, really crucial for the result that you get. Again, we have a denoising problem. The top left is what we would like to achieve. Bottom left is what we have. So this is our observation. And on the right, you see two different reconstructions for different lambda values. And you see that, tuning the value lambda is quite important. But of course, we can go further. This was just for one parameter. We can have also more parameters. We can even think about having a regularization term, which combines several regularization terms in the following sense, as it is given here. Again, the details are not so important. It's mainly that we have parameters that are a linear combination of filters. We have some other function rho applied to it, and then there's some more parameters. In fact, what you can observe here, you're all experts in machine learning, so you've definitely heard about neural networks. That can be interpreted as a one hidden layer neural network. You have already quite a few parameters. And we can push this also to the extreme case and have the data term and the regularization term both completely determined by parameters. It's just combinations of certain well-known terms, and you're interested in the weights, like in the neural network. But here, what I want to do is not end-to-end learning from a neural network input to output, but I want to have parameters that determine my optimization problem, and the output is the solution to the optimization problem. And in recent years, there's a research of interest in these kind of variational models, also just as a single layer in a deep neural network or a deep learning system. And in this talk, I would like to give ideas on what we can do, because for just one or two parameters, you can do a grid search. If you have 100 of parameters, there is also some probabilistic approaches that try to do some regression with Gaussian processes, which still works up to, let's say, 200 or 1000 parameters. But if you think about neural networks, at the level of 100,000 parameters or even more, so we should definitely use something else, and that is what I want to suggest, a gradient-based optimization. So this is our bilevel optimization problem. It is, as I say, just a formalization of the problems that we had before. So on the lower level, you have this optimization problem, which depends on parameter theta. We have here a long vector of theta values. And by solving the optimization problem, we get a reconstruction here denoted by x star. And the reconstruction x star is evaluated in the upper level via some loss function. Loss function, it includes some ground truth data, and comparing the reconstruction with the ground truth data gives us information on how to select the parameters in an optimal way. Okay, but there is situations where the problem is also non-smooth, and but let's forget about these situations for a moment. And we want to apply gradient-based schemes to solve this problem. And so what can we do? We want to compute a gradient with respect to the parameter theta. We want to find the optimal parameters. There are several options. You can like gradient descent. There's heavy ball methods, LBFGS, nonlinear, conjugate gradient methods, and there's even variants for the non-smooth state. Overall, the idea is you do an update step of, for example, I've picked one algorithm that we have proposed a while ago that uses the gradient and introduces additionally some momentum term, and it can deal with non-smooth functions by incorporating a proximal mapping. The important thing is it's gradient based. That means we have to compute the gradient of the loss function with respect to theta. And that involves, of course, the reconstruction x star of theta. And for this scheme, if you choose the step size alpha k and beta k properly, we can prove convergence of this algorithm. So we have a quite satisfying convergence theory for this kind of algorithm. But still, there's a practical issue. How do we compute the derivative of the loss function with respect to theta? Of course, if everything is nice and smooth, we can try to apply the chain rule. And this is what we do here on top. By applying chain rule, we have to compute the derivative of the inner function x star with respect to theta, and we need the derivative of the loss function with respect to the first argument, and of the loss function with respect to the second argument, the theta. And so the derivative of the loss function with respect to the first argument, it's not a problem. It's usually just measure the difference to some ground truth data b, then it's just this vector x minus b, and you're done. Sometimes you do not even have additional cost on the parameters, so the derivative of the loss function with respect to the second argument is directly equal to 0, and the remaining term is the derivative of the solution mapping with respect to the parameters. So, and that is studied in the context of sensitivity analysis in the context of optimization. But here, what can we do? We have the following situation. So in the following, we're just interested in computing the derivative of the solution mapping with respect to parameter theta. There's different strategies depending on the properties of the optimization problem. If the optimization problem E is, again, sufficiently nice and smooth, we can use implicit differentiation, which I'm going to explain on the next slides. We can approximate the optimization problem E by an algorithm, and it's often also called just unrolling of an iterative algorithm, and use automatic differentiation. So again, back propagation or extended chain rule, or we can even do some implicit differentiation on fixed point equations. So there's several options. And I'll also explain these strategies in the following, but before I start with that, I would like to give a warning that even if the function E is smooth, there is no need for the mapping x star of theta to be smooth. It can really be crazy mappings, and we have to think about that if we want to compute the derivative. And I insist on the fact that we want to have the mapping x star to be differentiable in order to apply these strategies, because otherwise we don't have any theory. We cannot guarantee what kind of derivative we get if any of the ingredients, any of these functions that we have to evaluate is not differentiable. So there's problems if E is differentiable. There's even more problems if E is not differentiable, problems that you face often in machine learning. And moreover, if the solution is not even unique, then there's lots of problems. So we have to be in a very controlled setting in order to do something. The first strategy is implicit differentiation. And that is based on the starting point that we can write down optimality condition for the optimization problem. Just as you know from classical calculus, just take the derivative of the function, set it equal to 0, and find the points x that satisfy this condition. This equation here defines as implicitly a function x depending on theta. And so we can assume that there is a function x of theta and apply the implicit function theorem to get a closed form expression for the derivative of x star with respect to theta. And that expression involves the Hessian matrix of E, Hessian matrix of our objective in the optimization problem, and some other second derivatives of this objective function. But the most important and most expensive thing is that we have to invert the Hessian matrix or solve corresponding linear systems of equations. And of course, this has quite some disadvantages. Solving a linear system of equation just to compute a gradient is quite expensive, and it's actually also not very stable, especially if the Hessian matrix of E is a singular matrix. Eigenvalues are also close to 0, then it's really problematic to do this and to reliably compute the derivative of the solution mapping. An alternative approach is to replace the algorithm by the optimization problem by an algorithm. So instead of looking at the solution mapping x star of theta, we look at the algorithm that we start at some initial point and we run it for a fixed number of n iterations. And this gives us an explicit mapping from the parameter theta to some approximation to the solution mapping, which we can differentiate if the algorithm is differentiable, of course. Then again, we apply a chain rule, and that leads to the backpropagation algorithm if we combine it with what we've seen before. The good thing is this approach gives us always a unique solution. It's not always the unique solution of the optimization problem, but it's a predefined mapping from input to n iterations of the algorithm, and it's clear that this will always be the same. Okay, after we fix the algorithm and the number of iterations, this approach is exact in the sense that we differentiate the algorithm, and by doing the chain rule, by doing the backpropagation, we follow the right process as suggested by theory. And what is nice, we can even prove that the sequence of derivatives that is generated by this process, it converges to the derivative of the solution mapping if we send n towards infinity. And beyond that, we can even prove that for algorithms that are faster than standard algorithms, so-called accelerated algorithms, also the convergence of the derivative sequence is also accelerated. Of course, as you know it possibly from backpropagation, this process requires to store all the intermediate iterates and can therefore be quite memory expensive. But there's also a remedy for that. And that can be motivated by looking at the fixed point equation. So we assume that the algorithm converges to a fixed point, meaning that this kind of equation is satisfied. If you apply the algorithm again, then you're not changing the current point x star any further. By implicit differentiation, as we have seen it in the first strategy, but now applied to the fixed point equation, we get this kind of expression for the derivative of x star with respect to theta. And now if you do some expansion of this resolvent that you see here, this identity mean minus the Jacobian of A with respect to x star, can do some expansion with the geometric series and you get an expression like that. And if you translate it back, then you see it's exactly the same as applying an algorithm for n iterations but you do not store the intermediate results. You just always use the final one. At first glance, it looks like you're making an error because you're making backpropagation, but you use the wrong point at intermediate stages, but that can be motivated. And it's actually a quite good strategy. And it's, there's even situations where you can prove that it actually converges faster to the derivative of the solution. Okay. And yeah, finally, I just want to motivate what we are interested in beyond what I've shown so far, namely if the optimization problem E is even non-differential. That is, as I said, is quite often the case in applications of machine learning and computer vision. So it's not even clear what we want to compute, because if the solution mapping X star is not differentiable, so what do we get? What do we want to have? There are still strategies that ignore the differentiability issue, and there's also ways to explain it by weak differentiation. It's also a good explanation, but if you use these kind of weak derivatives, we don't have a converging algorithm. There's no convergence theory for the gradient-based algorithm that we use for finding the optimal parameters. Again, you can do the unrolling strategy, implicit differentiation strategy, and there's a really interesting setting. You can have a non-smooth optimization problem, but you can formulate an algorithm which has an update mapping that is given by smooth mappings. So you can replace this non-smooth optimization problem by n iterations of a smooth algorithm. And you can do the backpropagation, and you do the proper computation of a chain rule, and in this way, you at least compute proper derivatives. We have no idea what they converge to. Of course, that's a difficult question because we have some non-smoothness involved. Okay, I do not want to go more into detail. The key idea for doing this reformulation are Bregman distances. Change the geometry of the space, and then we can do this kind of reformulation. If you're interested, I can refer you to some papers where this is shown. Leads me to the conclusion. We have I've tried to introduce a bilevel optimization framework, which is, for me, first of all, a formalization of the parameter learning in general, gives us a basis for formulating abstract algorithms for which we can prove convergence. And I've shown several strategies to run these kind of gradient-based algorithms, which require computing the derivative of the solution mapping with respect to the parameters. These strategies like implicit differentiation, weak differentiation, unrolling of algorithms, and also implicit differentiation of fixed point equations. So that's it from my side. Thanks for the attention, and I'm ready for some questions.